Welcome to day 20. We are going to be talking about changes in temperature and phases today. So let's go ahead and start, and let's look at our ISM book and our textbook. So in this section here, we are going to, in our textbook, we're going to be talking about change in temperature and the phases. Specific heat capacity is the main idea here. To be able to define the specific heat capacity, there is a number that we would be using. If you look in your textbook on page 316, it will actually give you, for whatever item that it is, it will give you what the specific heat is in joules times kilograms times Celsius. So when we're talking about specific heat capacity, that is the quantity of heat required to raise a unit of a mass of a homogeneous material, 1 kilogram or 1 Celsius, in a specific way of giving a constant pressure and volume. So, each of your substances will have a unique specific heat capacity. So we are going to be using this formula here. Cp, which is specific heat capacity, equals Q, which is energy, over M times change in T, which is mass, times the change in temperature. So we have a subscript of P, which is specific heat capacity, is measured in constant pressure. So here I drew a picture of what a calometer looks like, and also the formulas that go along with it. These two formulas here are the ones that we're going to be using in this section. These are the two that you need to know. I want to make sure that you understand, even though they have a lot of subscripts here, it isn't that hard once you start, but there are some steps that you will have to go into to find some of these answers first before you put it in the big equation. And a calometer is an experimental procedure used to measure the energy transferred from a substance to another in heat. So, on page 317, what they do is they give you a scenario, and it says that a 0.0050 kilogram metal bolt, so that is what we are starting off with, that is our metal bolt here, is heated in an unknown initial temperature. Then it is dropped into the calometer that contains 0.15 kilograms of water. Well, there's our mass in water. And initial temperature is 21 degrees Celsius. Well, that is our temperature of our water. If the metal is specific heat capacity of 899 joules per kilometer squared, that's where I'm getting that number from here, find the initial temperature of the metal. Well, the metal that we're using is a metal bolt. So if you look on the left-hand side for a metal bolt, you will find this number here. And this is my ending number. So what you're going to do is, the first thing they did was draw a scenario of what it shows. And then what they did is they went in and they went through several steps to find this one formula that we're doing here. So if we're doing this formula here, the first thing we want to do in our calculator, we will want to make sure we're in scientific and we're going to be in radian, because we're not doing any kind of cosines with this. So this is alpha y inner. And so we have an open bracket 4186 close bracket. That is our mass. And we're going to times that by 0.15. That's going to be for our water. And then we're going to go and take the initial temperature. Your final temperature was 25 degrees Celsius. And you're going to subtract the initial temperature was 21 degrees Celsius. Then we're going to go down. And then we're going to go and we're going to have and take our specific heat for that metal, which is 899 joules. And then we're going to multiply that by our mm, which is our mass of our metal. So we're going to open bracket 0.050 close bracket, and we're going to go over and we're going to hit enter. And when we do that, we still have one thing left to do. We have to add that to 25 degrees Celsius. So let's go back up. Let's go back in. And let's go ahead and add 25 degrees Celsius to that. And we're going to hit enter. And when we do that, we get 80.875417, which in our case we would round it up to 81 degrees Celsius. So now what we're going to do is we're going to go on to page 318, and I'm going to do problems 1 and 3. You will need to do 2 and 3, 2 and 4 on your own. So the first one says, what is the final temperature of a 3.0 gold bar? There's my gold bar. Dropped in a 99 degrees Celsius into a 0.22 kilograms of water, and it has a temperature of 25 degrees Celsius. And so we have to go and find on our paper the specific heat for that metal. And here we are with all our equation. But as you look over here on the right hand side, you will see this is my equation that I'm going to be doing here. But to get these answers, I will have to break this down a little bit instead of chugging all this in, because that's such a big formula. I'm going to start with TWCP WMW first. So what I'm going to do is I'm going to take my 25 degrees Celsius. I'm going to multiply that by my 41865 kilograms per Celsius. And I'm going to multiply that by 0.22 kilograms. And once I do that, I get 2.3 times 10 to the 4th power. Then I'm going to do the next section, which is this one here, CPW. So I'm going to have 129 joules times 3 kilograms, which would give me 390 joules per Celsius. And then I'm going to go and find my TGCPG.mg, which I'm going to take my 99 degrees again, multiply by 129, multiply that by 3 to get 3.8 times 10 to the 4th. And so then what I'm going to do is I'm going to take now my answers that I have broken this down, and I'm just going to put it in a calculator. So it is a fraction, so I'm going to do alpha y equal. I'm going to do 2.3 times 10 caret to the 4th power over, and I'm going to add 3.8 times 10 caret to the 4th power. I'm going to go down to the bottom. I'm going to do 920 plus 39D. And then I'm going to go over and I'm hit enter, and I get 46.56, and I rounded it to 47. For number 3, it's a little different because it says brass is an alloy made of a copper and zinc. 59 kilograms of brass at 98 degrees Celsius is dropped into a 2.0 kilogram of water at 5 degrees Celsius. If the equilibrium temperature is 6.8 Celsius, what is the specific heat capacity of the brass? So we're only wanting to find the brass part of this. So for this one, we have our metal of our brass, our temperature of our brass, and then our measurement of our water. And then we're going to get our specific heat that we're going to get from the other page for the brass. And this is the formula that we're going to be doing. But as you can tell, we're going to take it and chunk it, where we're going to do small chunks of it. So the first thing that I'm going to do is I'm going to find this part here and this part here. To be able to do this, when we have the change in, remember, that right there, the change in temperature of the water, you're going to have to do, the before and the after of both. And that's what they're doing here. So they're trying to find the temperature of the water first. Then they're going to try to find the temperature of the brass second. And then once we get that, we can go back up here and plug this in to our equation. And you should get 390 joules per kilogram times Celsius. Now, and the last thing I want to talk about is latent heat. So in the book, it shows an ice cube that goes from ice cube to boiling point. So as you can tell, it's going through phase changes. So we start with here, temperature of the ice is increasing, and then the ice melts and becomes water, and then the temperature of the water increases, and then water starts to boil, which produces steam at the end, and that's what is showing here on this graph. Phase change is where a physical change from a solid, liquid, or gas to another state. Latent heat is the energy per unit mass that is transferred during the phase change of a substance, and we have Q equals mL. And there is also in the book a picture on page 320 about different substances and at what point does it melt, does it boil, and how does it change.